and welcome to Acoustics Derivations. In this video, we will derive the impedance of a spherical wave. So before we begin, what is impedance again? Well, in acoustics, we often encounter the specific acoustic impedance, which for this video and pretty much henceforth, unless otherwise noted, we'll just call the impedance, and that is pressure over particle velocity, P over U. Okay, so we want to find the impedance of a spherical wave. So let's let pressure be some function f of t minus r over c naught over r. So that's an outgoing spherical wave general solution. Now, let's suppose that f of t is some constant a, or some amplitude a, I should say, which is a constant, but some amplitude a times sine of omega t. Therefore, P is equal to a over r times sine of omega t minus omega r over c naught. And we note that k, which is the wave number, is omega over c naught. So P becomes a over r times sine omega t minus kr. Now, this is a bit unwieldy to work with, sines and cosines. It's a lot easier to do a lot of acoustics math if we do it in terms of complex exponentials. So we note that e to the I theta, e to the j theta, that's the convention I've assumed here, e to the j theta is equal to cosine theta plus j sine theta. So pressure is really, or it can be represented now as a over r times the imaginary component of e to the j omega t minus kr. So we're going to actually write then, stick with this, as a over r times e to the j omega t minus kr, where we assume the imaginary part. The imaginary part is assumed. Okay, so once we have our expression for a spherical wave shown here, now we need, if you remember, we want to find impedance, so we need P over U. So we have P and we need U, right, to find the acoustic impedance, or the impedance, the specific acoustic impedance. To do that, we recall the linearized momentum equation. Rho naught du dt is equal to negative dp dr. Okay, well, dp dr is pretty easy via chain rule. It's negative a over r squared e to the j omega t minus kr minus j k a over r e to the j omega t minus kr, which can be rewritten as negative 1 over r plus jk p. Okay, so now we need to turn to particle velocity. Well, if P is proportional to the e to the j omega t minus kr, then physics dictates, or physics tells us, that u is also proportional to e to the j omega t minus kr. Thus, we can note that the time derivative of particle velocity is simply j omega u, some arbitrary function u, which is proportional to e to the j omega t minus kr. If you take the time derivative, you get j omega u. Thus, the momentum equation tells us that j rho naught omega u is equal to negative, the negatives will cancel. The negative from here and the negative from here will cancel. 1 over r plus jk times p. Okay, and then we can solve for u simply as 1 over j rho naught omega times 1 over r plus jk times p, which can be rearranged to be, if we take out a jk from both of these in the bracketed terms, we get 1 over rho naught c naught. Again, k is omega over c naught, so that can be rearranged. So we get 1 plus 1 over jkr p. Okay, well then we are there. So we have z is equal to p over u, which is going to be rho naught c naught over 1 plus 1 over jkr. So that is, and maybe I could subscript this as spherical. This is the impedance of a spherical wave. Specifically, I should say a spherical time harmonic wave. Now, what if, so this was for an outgoing wave, but what about a converging wave? Well, it turns out that the spherical impedance for a converging wave, a converging spherical wave, is very similar, but given by that expression there. So turning back our attention to the specific acoustic impedance of a outgoing spherical wave, we do a little bit of analysis. If Kr is much, much greater than 1, then the specific acoustic impedance of the spherical wave is just rho naught c naught, which, if you saw the video on characteristic impedance, you will know that that is just the characteristic impedance of a plane wave or of a medium. So if you're far enough away, the waves appear plane wave-like, the spherical waves. But if you're really close to the source, turns out that z is jkr rho naught c naught, which is purely imaginary. It's purely reactive. Okay. One final note before the video ends. So if you remember at the beginning, we assumed that p was a function of f of t, where f of t was a sine omega t, made the substitution in and said, okay, well, we only want to take the imaginary component of the complex exponential. What is the particle velocity then? What is the physical particle velocity? What is the physical particle velocity? U. Well, just like pressure was the imaginary component of the complex exponential, same will be particle velocity. So we're looking for u, and the imaginary u is the u we calculated above, which is equal to the imaginary component of pressure over the spherical, the impedance of a spherical wave, which turns out to be oops, I dropped an R there. My apologies. Rho naught C naught R, which turns out to be, if you were to take the imaginary component, U is equal to A over rho naught C naught R times sine of omega t minus kr minus 1 over kr times cosine omega t minus kr. So that's our expression for the real physical particle velocity. So again, the big crux of this video was deriving the impedance of a spherical wave, and that was found to be rho naught C naught over 1 plus 1 over jkr. So that concludes this video. Thank you.